In this example, a ball has been thrown vertically into the air with an initial velocity of 3 meters per second from the top of a tower 15 meters above the ground. In the first part of the question, they're asked to determine the velocity of the ball after 2 seconds. Before we can do that, we have to start by finding the equation that describes the height of the ball with respect to time. That equation is h equals 15 plus 3t minus 4.9t squared. This equation, or function, is obtained from the formula h equals h0 plus vit minus 4.9t squared. This is an equation that you should have seen in your grade 12 math course, because there were a lot of problems which involved throwing objects vertically in the air. This equation is actually derived from the physics formula displacement equals VIT plus 1/2 AT squared. Once we have this formula, where h is the height and t is the time, we can take its derivative and obtain dh dt. H really in this case is the displacement. So we could say that this derivative is ds dt if you wanted to. That way it makes it a little more clear to yourself that this particular derivative is indeed the instantaneous velocity of this object. When we take the derivative using the power rule, we obtain 3 subtract 9.8t. Then it's simply a matter of substituting the time, 2 seconds, and we obtain negative 16.6 meters per second. This is the velocity of the ball at 2 seconds. Since this velocity is negative, it indicates to us that the ball is returning to Earth at this point in its trajectory. In part B of the question, they ask us, when will the ball reach its maximum height? Now, there are 2 different techniques we could use to solve this. One technique was a procedure that you learned last year in your grade 12 math course. Since we're dealing with a quadratic function, we could simply find the x-coordinate of its vertex using the formula negative b divided by 2a to obtain the desired time. And that would be fine. But we're going to take a slightly different approach. We're going to use our knowledge of calculus to solve that same question. If you remember back in the previous part of this question, we said that dh dt was the rate of change in the displacement with respect to time, or the instantaneous velocity. When the ball is at its maximum height, its velocity is momentarily equal to 0. So if we take the derivative, 3 minus 9.8t, and set it equal to 0, we should be able to find the time when the ball reaches its maximum height. And that is exactly what we've done. We've rearranged and solved for t, and t is equal to 0.31 seconds. In the third part of the question, or part C, we've been asked what is the acceleration of the ball at 1.3 seconds. Well, the first derivative is the velocity. Therefore, if we take the second derivative of the original function, that would give me the expression for the acceleration. So we've taken the second derivative and obtained negative 9.8 meters per second squared. What we see is that our acceleration is constant, regardless of what time we use. This should make sense, since gravity is acting upon the ball, and therefore the gravitational acceleration should be constant. In part D of the question, they ask you what is the ball's velocity when it strikes the ground? Well, the first thing we should do is find out when the ball strikes the ground. So we take our equation, h equals 15 plus 3t minus 4.9t squared, and we substitute 0 in for h, because when it hits the ground, its height would be 0. It's just a matter of simply solving that quadratic equation. In this case, we've solved it using the quadratic formula because factoring doesn't work. And we obtain two solutions, negative 1.47 or 2.08. Well, obviously the 2.08 is the correct answer. So then we want to take that particular time and we want to find the velocity at that time. Well, the velocity is dh dt, and we had already worked that out in previous questions, and it was equal to 3 subtract 9.8t, and then we just simply substitute in our given time, 2.08, and we obtain the velocity of the ball when it strikes the ground, which in this case is negative 17.38 meters per second.